Okay, so our next lecture is going to be about acid and bases. And so biologic systems are going to take many steps in order to ensure that their hydrogen ion concentration does not change, since even minor changes in the acid-base can have dire consequences. And we're going to talk a little bit about these. And so basically we have our acid and bases. So what are they? Bronsted-Lowry definition is a very well-recognized definition. And so according to this, what is an acid? And an acid is an increase, or an acid is a proton donor. And so this is going to lead to an increase in hydrogen into a solution. And so therefore you are going to decrease the pH. And then what is a base? In essence, a base is a proton acceptor. And so this is going to decrease the hydrogen in a solution. And so this results in an increase of pH. So for an example is acetic acid. Oops. And acetic acid is found in vinegar, and it is a weak acid. So it partially dissolves in an aqueous solution, and so you have sort of an equilibrium. So acetic acid in an aqueous solution is going to break down to some degree. Into the hydrogen ion and an acetate ion. And of course, hydrogen ion. And so the double arrows indicate that it does not completely ionize. And so this acetate ion is a base. It can, in fact, accept a hydrogen. And then, of course, acetic acid is the acid. And so these two species are going to be a base pair. So they are a conjugate base pair. And conjugate base pairs differ by only one hydrogen. Okay, so now in general, an acid is going to give up their hydrogen ions when in water. So we have hydrogen chloride, which is a proton donor, and then we have water, which is going to be the proton acceptor. And so hydrogen chloride is a strong acid, so it will dissociate in water. So acids are typically going to be more sour tasting in our foods. So our vinegar, oranges, lemons, etc. are going to be more acidic. Bases are going to act as a proton acceptor, and so ammonia, for example, can accept a proton and become the ammonium ion. And this has a two-way because it's going to be an equilibrium, whereas hydrogen chloride is a one-way because it's a strong acid. So in water, it will dissociate completely. Now, bases are going to have more of a bitter flavor, so your caffeine, nicotine, it also is going to be found in soaps and cleaners. Now, water is both an acid and a base, and remember, water has a polar nature. Oops. And so water can attract and soak up other polar molecules. So it is the universal solvent. Of course, we have hydrophobic, which means water-loving, and hydrophilic, which means water-hating. And water, of course, is going to be in some sort of equilibrium. Water can act as a proton donor as well as a proton acceptor. And oftentimes when you write chemical equations involving water, you don't actually include water in the chemical equation. It's just assumed to be there. So sometimes you don't see it. Usually maybe just an aqueous environment on the arrow, for example. Now, just a little bit of overview about acids and bases. We have 6 common strong acids, so hydrogen chloride, hydrogen bromide, hydrogen iodide. We also have nitric acid. We have sulfuric acid. And we have perchloric acid. So hydrogen chloride in an aqueous environment becomes an acid. Same with bromide, same with iodide, etc. We also have several weak acids. Hydrogen fluoride. We have ammonium ion. Ammonia is toxic to cells, and so rapidly becomes ammonium ion in our bodies. We have acetic acid, carbonic acid, which we'll talk about, and we have nitrous acid. Now, ammonia is, as I said before, toxic, and ammonia actually can move around the body, can move through your cell membranes. The ammonia ion is not toxic, and it's charged, so it cannot move into and out of cells because it can't get through the lipid bilayer, whereas ammonia can. So at a physiologic pH in the body, ammonium ion is favored. And ammonia is not favored. Now, weak bases are not going to be very soluble in water. And of course, ionization, as we saw, of hydrogen chloride is going to be complete. In an aqueous environment, okay, so now let's talk a little bit about what we mentioned earlier, which is conjugate acids and bases. So again, these are going to be 2 substances that differ only by a single hydrogen, and they're referred to as conjugate pairs. And so we have our hydrogen sulfite as an example. And so hydrogen sulfite, if it becomes sulfurous acid, SO3, this is going to be a conjugate acid. And then if you're going to take away a hydrogen, you're going to have a conjugate base formed, sulfite ion. And then another is going to be hydrogen phosphate. This is a very important one in our cells to buffer our cells intracellular. And then hydrogen phosphate is going to become dihydrogen phosphate, which is its conjugate acid formed. And then its conjugate base is going to remove that hydrogen and it's going to become phosphate. Now, what's important about hydrogen phosphate is it does have a parent species, phosphoric acid. And phosphoric acid is H3PO4. And so in essence, there are 3 hydrogens that can possibly be donated. And so this is called a triprotic compound. Proton. But it can only donate 1 hydrogen at a time. So over here, for this species, we have one hydrogen left, and so that becomes the phosphate if it donates that hydrogen. Here, oops, all right, we have two hydrogen left, and so it can potentially donate two hydrogens. And then the phosphoric acid has three hydrogens that can potentially donate three hydrogens. And we also have a sulfate ion as an example. Now you can see a sulfate ion does not have a hydrogen, but it can accept a hydrogen, and it becomes hydrogen sulfate. Or bisulfate. And it has no conjugate base. So it is not able to donate a hydrogen since the sulfate ion does not have a hydrogen to give. And it's the same thing with a phosphate. The phosphate does not have a conjugate base. It does have a conjugate acid, which is going to be a hydrogen phosphate. Okay, so this is just an example of what conjugate acid and base pairs mean. Now let's talk about our equilibrium reactions and our dissociation constants in aqueous environments. So the dissociation constant is referred to as K, and this is going to measure the strength of your acid base. So we have the acid, and we have our base, and we have our conjugate acid, and we have our conjugate base. And so your K constant is going to always be the products over the reactants. So here we have our products, and here we have our reactants. And the equilibrium reaction uses what's called a mass action expression. This is also known as the equilibrium constant. Or the reaction quotient. So all of these are interchangeable: mass action expression, equilibrium constant. And so these are going to be used as long as there's the balance between the species is going to be present during the reaction. Now we have a Ka, which is simply the acid dissociation constant. And so again, for the equation, you're going to have the reactants becoming the products. And so your Ka is going to equal the products concentrations over the reactants. Now the brackets are resembling the molar equilibrium concentration. And if your K is going to be 1, then this is going to be a strong acid. So basically it's a ratio. So you're looking at the ratio of the products in comparison to the reactants. So if the products are in excess, that means the reactants are breaking down more because there's more product, less reactants. And so a higher number divided by a smaller number is always going to be greater than 1. And it's, of course, going to be the reverse for a weak acid that doesn't want to dissociate. The products are going to be lower than the reactants, and so you're going to have a number less than 1. Now, base dissociation has the same kind of concept. You have your base plus your water, and you're going to get your conjugate acid. and your conjugate base. And the Kb is going to be the same product over reactant. So Kb greater than 1 is going to be dissociation favored. You have more product than you have reactant. So every acid has a Ka, and every corresponding conjugate base has a Kb. So what this means, the Ka and the Kb of a conjugate acid-base pair remember, those are only differing by hydrogen, are related to the Kw or K water. Kw is the ionized state of water. Okay, so the water dissociation constant. So there are two sort of constants here. We have an actual dissociation constant, which is the Kd, and this is simply your products over your reactant. And this is approximately 1.8 times 10 to the negative 16. And so what that should tell you is that water is favored in an aqueous solution rather than that it dissociating into the ions, hydrogen ion and hydroxide. And so the Kw is the ion product of water. And so this is basically the concentration of your hydrogen ion and your hydroxide ion, which is approximately 1 times 10 to the negative 14. And so one thing to keep in mind, this is going to be a constant. And so what it means to be a constant is, therefore, here's my therefore symbol, when you increase your hydrogen ion concentration, it requires an increase of your hydroxide ion concentration. So for every conjugate acid-base pair, you're going to have some sort of constant associated with water. So Ka, Kb equals Kw equals 1 times 10 to the negative 14. Now, so what we're all getting at is, of course, trying to relate everything back to pHs. And so water has a hydrogen concentration of 10 to the negative 7, the 7 got put over here. And so this is a pH of 7 because pH is the negative log of your concentration of hydrogens. And so the negative log of 10 to the negative 7 is 7. Now, one thing to keep in mind is on a pH scale, this is a 10-fold scale. Okay, so we're not just simply going in a linear fashion here, it's actually a 10-fold scale. So from going 7 to 6 or 7 to 8, you're changing the hydrogen concentration 10-fold. Also keep in mind with respect to the pH that this is open-ended. Okay, so pH scale is open-ended. Even though most of the time we show it from 0 to 14, you can have some compounds that have a negative acidity, for example. Hydrochloric acid, 1 molar, is going to have a pH of -1. So it's not a finite scale, just so you know. And pH neutral, of course, is going to be at that 7. So here's a list of strong acids, and all of these are going to dissociate completely in an aqueous environment. They're all going to be good proton donors. We have the ones we talked about earlier. And here are our strong bases. And again, these will ionize completely in water, so they're going to be good proton acceptors. Now let's talk a little bit about our relationship of P of K to another value called pKa. So pH is measuring our concentration of hydrogen. We know that. And pKa is referred to as an acid dissociation constant. pKa's relationship to Ka is that pKa is the negative log of Ka. So in essence, they're going to almost be reciprocals of each other, and we'll talk about that in just a moment. pKa, the dissociation, tells you the pH needed for a chemical species to donate or accept a proton. So for a chemical species to dissociate, get rid of its proton. A low pH with respect to hydrogen concentration means an increase of hydrogen concentrations. A thing to keep in mind is that the lower the pKa value, the stronger the acid. And this is going to be opposite of Ka. So it's the higher the Ka, stronger the acid. So here's a table of some acids and pK values. And so again, you can see that we have our Ka scale and we have our pKa scale, and they're going to be opposite of each other. So our strong acid down here, our hydrochloric acid, which is a strong acid, and our carbonic acid up here, which is a weak acid, and everything in between. For our strong acid, you have a very high Ka and a very low pKa. And our weak acid, you have a very low Ka and a very high pKa. So they're opposite of each other. And so keep that in mind and pay attention in a test type question. If you're being asked or you're being given the Ka value or a pKa value and being asked if this is a strong acid or strong base, or weak acid, weak base, whatever. Okay, so now why is all this important? Okay, so we know that a pKa value will tell you if you have a strong acid or base. And so one thing to keep in mind that this is important in our drugs. So drugs are either acidic or basic. And so an acidic drug needs to be absorbed in an acidic environment. And a basic drug absorbed in a basic environment. So a lot of drugs you ingest, you take in orally, and so these would be in the acidic range because they need to get absorbed in your gastrointestinal tract, your stomach. There can be some neutral drugs that get injected into your blood. So it depends on where the drug needs to be delivered as to whether the properties of that drug need to be acidic and or basic. Now we have a percent ionization calculation. And this is going to be 100 over 1 plus 10 to the x times pH minus pKa. Okay, so anytime you have a power 2 something and you have a negative symbol in here, that negative symbol is going to drive the actual number of that x value, if it's going to be a negative x or if it's going to be a positive x. So if this x here is negative, then it's going to be acidic. If the x is positive, it's going to be basic. Now, others that are important to keep in mind about all this is we have some substances that can act as acid or bases. So those are amphoteric. And so an important one is going to be our bicarbonate system. This is going to be the major buffer of your blood. So we have bicarbonate. That can act as either an acid or a base. So in this case, it is donating a proton, so this is being an acid. In this case, it's accepting a proton, so it's acting as the base. And so your bicarbonate can be either acidic or basic. And so it can be, in essence, its own buffering system. Now, amino acids can also buffer. So amino acids are going to have a basic amine. And they're going to have an acidic carboxyl group. So your basic amine can pick up a hydrogen, and your carboxyl group can donate a hydrogen. So for example, these can be either an acid or base. So if we take glycine, it's easy to write. You have your amine side, another carbon, and then your carboxyl group. And this can be broken down into a hydrogen ion. With now a negative charge on that carboxyl group. Alternatively, and this can lead to a picking up of a hydrogen. And in this case, is acting as a base. And some amino acids can even transfer a hydrogen from the carboxyl group to their amine end and form a neutral species. So this is referred to as a zwitterer ion. And so in this case, you will have your glycine, and so this is considered neutral because the positive charge and negative charge cancel each other. Okay, and so that is the end of our acid base.